So I'm going to present something on fracture and curvature, and in particular on curvature-induced fracture in two different scenarios. One is for thin rods, and one is for thin plates. And everything I'm going to present on thin rods is joint work with Jiri Seemann, who was also funded by this SPP in the first funding period. And anything on plates is joint work with Mario Santilli, who's a former postdoc and is now Okay, so we all know that fracture of thin. Yeah, so here's next brief outline. First, some general words on curvature and fracture. Then basically this kind of background material, and then the rods and membranes and plates. So you all know that fracture of thin structures is important to understand. Of course, I mean that's a thin structure and it breaks, and that's unpleasant. But in fact, it's not really the model I'm interested in, because it does not have so much curvature. But instead, there are structures which are very, very thin, and they can undergo very, very large curvature. This is certainly a finite bending regime where this tree is in. But you also know that if you push this a little bit further, then it's unpointable fracture, and it will have curvature-induced fracture. Okay, so that's basically how these things look in 1D. In 2D, there's another, it's a bit more like a fun application here. So it seems there was some discussion that even iPhones have a soft bending mode somehow. So you could bend it. It's the iPhone 6. I think you can bend it a little bit, which is suboptimal for the glass cover if you do it. But somehow it's in the wrong way, it appears that. So, but this is now a structure of a thin plate, right? It has two elongated directions in this case, and a very appearance that it can bend, and if you bend it too much, it can fracture. Okay, so let's come to a bit more serious applications. So now first for thin rods. What is the prototypical example of a very, very thin rod that can undergo finite bending and fracture in the end? And we all know that this is a typical phenomenon. This is happening to spaghetti. So if you take spaghetti, and you really see it's a finite bending regime here. If you overdo it, then at some point you will have fracture. And this is exactly the regime I would like to understand a bit better. In fact, I'm having a recent postdoc now from Italy, and he says that this experiment is a crime. Okay, so this is well, we also have another experiment here. So this is by other people, and this is exactly very much the specimen I would be interested in. It's a ceramic nanowire, so that's a zinc oxide ceramic structure here. Here you can see it, and if you pull a little bit here, you see that this bar really bends. It's only tens of nanometers thick, and it goes into a finite bending regime, although it's very, very brittle, but it's also very thin at the same time. And then, at some point, if it's too curved too much, it cracks here. And for these very, very thin structures, which are really like single crystals, what's happening is they really crack by cleavage. So they cleave along a crystallographic hyperplane, and then they fail, and this is what's happening. And this is exactly the kind of models I would be interested for the rod case. Now, of course, there's also, and since we're here in the beginning, setting the stage, so what would be the analog in the 2D case? So if you have two extended dimensions like a plate, but then of course it's not spaghetti, but you have to bend lasagna. Here, so you see also that there is really a finite bending regime, right? Okay, it's a suboptimal probe, it's more like a shell actually. But so there's a finite bending regime here, and if you overdo it, at some point it simply breaks. And this, in fact, gives you an interesting modeling issue here. So this is again a different probe. So this is a glass. This is Gorilla Glass, and it really undergoes finite bending because it's so very, very thin. If you did this with the window here, it would immediately crack, right? But this glass is so thin that in fact it undergoes finite bending. And this is a difficulty from the modeling point of view, because it tells you the following, that if you just make this very, very brittle material, and here maybe this guy is even more brittle, if you just make it thin enough, and thinner and thinner and thinner, eventually there will be no fracture because it's too thin. So you should not really think about the thickness, but maybe it's also much better to think about the aspect ratio. So you can make it thinner and thinner, or otherwise you can leave the thickness and can make it longer and longer, right? And if you did this longer and longer, in the end you could really wind it up and it would never break. It would be purely elastic. So what we're really after, and that's a bit the difficulty later in modeling, we are looking into effective descriptions where the thickness somehow scales with certain material parameters which set basically the fracture toughness. So the fracture toughness, what we are interested in the regime, the fracture toughness has a non-trivial interaction with the aspect ratio. Okay. Now, that's the first slides. Now let's go to some background. So now the more boring slides. So this, as you all know, is really elasticity. If you deform a body, it's more to set a certain notation here, right? So W will be my stored energy function all the time. It has the usual assumptions. So it's usually, if you assume it's minimized exactly at the identity, and then by frame indifference also at all of SO3. Then you assume it to be as nice as you wish. And typically we also assume that it has a non-degenerate energy well at SO3, and it satisfies also some maybe global assumptions, growth assumptions from below. Now if you do this, and then in fact you're looking at probes which you cannot distort too much. If you look at small strains only, then you should linearize, and that's what we will do. So if you have small strains, meaning that the strain is almost the identity, you can plug this in where you can do a polar decomposition of the gradient here, and then you're left with this guy by frame indifference. And then basically only this small strain here enters the picture, and what is left here from the Taylor expansion is only the elastic moduli, which are nothing but the elements of the Hessian of this W function at the identity. Okay, so that's my Q, which will appear later again. Okay, now what are the thin structures? So there are two kinds of thin structures. There are thin films. So thin films would have finite extension in two directions and a small height. So that would be like the mid or the ground plate. And thin bars would have a long elongation here and a small cross section. And H is always very small. It's the aspect ratio. And then, of course, it's interesting because you have very nice new phenomena. You can do with little energy. You can do a lot to these thin structures. Now, it's a very classical theorem, and I think that most of our line of research, I think most of you know this very well. There's a whole different kinds of things that can happen. So, for example, if this guy were made out of rubber, and I really push and pull here, and I distort it in a finite way, so I have finite energy per volume, which is in this case for a membrane, or this case for a thin rod, then this would lead to a membrane theory. So this would be described by so-called membrane deformations. But on the other hand, if you're, and we will be also interested in this curvature-induced regimes here. Now, if you look into something where you take a plate and you bend it in a finite way, then you will see that the strain itself is like the aspect ratio, and which then, if you the energy is then it has a squared, and then the volume has another h. So basically, you end up with energy at scale like h3 for plates, and this would be precisely deformations which show finite curvature and finite bending. And for the rod, you lose even another power of h, or win another power of h. Now, this is now being well studied for many years now. What you want to do is you want to relate the nonlinear elasticity function I had on the last slide to some reduced energies here, which only take which as their variables only take the in-plane variables here, or say the one direction of the rod here. You would like to derive effective membranes and strings and plate theories, and this is classical works. So for our case, interesting is the work of Ledet and who did this in the membrane regime, and then you all know about this result of James and Müller for the plate theory, and in particular for us it will be important to look into this results by Maria Giovanna and Stefan Müller for the rod theories. Okay, so that's good for elasticity, but somehow we need to do fracture as well. And here, if you want to do fracture, you cannot live with cellular functions, but instead you all know we have to look into SPV functions. If you don't know, these are just guys that can jump on a codimension 1 space. And instead of a pure inertia, that is my energy functional here. And now I have to augment this by some Craig energy contribution. So this is exactly as before. And here I get another integral over the Craig set, where this is basically, this psi is something like the Craig energy per surface area. And so in the brittle case, in the most easy case, I'm getting here something like this, which basically tells me how big the Craig is that I have introduced. Right? And then this would be called the Griffith-type energy functional, and this is the kind of variational functions, the variational description of these at the same time brittle and elastic materials. Okay, so far for the variational to set the stage. Now let's go into atomistic models for nanowires. Now to recall, so these nanowires, this is the kind of deformation. So we want to see finite bending and also finite torsion, as it will turn out, and fracture at the same time. And it should be atomistically thin. And the question I would like to answer is, no, not this one, but this. So here is such a thin rod, and you can see here it consists of very many fibers of atoms and has a certain cross section here and this elongated direction here. And now you look from further and further apart. In the end, you will see only this one line here, and basically you would like to have an effective theory which only takes basic one-dimensional rods as an ingredient, and tells you what is the rod energy if I distort this rod a little bit. And we would like to do this in a rigorous way, so we would like to identify a gamma limit. So because of this, I somehow have to start by giving you the energy. So what is the energy? I have one slide of bookkeeping. So this is the rod. If you look from far apart, what you will see this. We have seen this on the previous slide. This macroscopic region, which is occupied by the rod. But in fact, you're not interested in all of this, but only in the atomic lattice sites. And for the sake of simplicity, let me take this as a cubic lattice. So I have a small cubic lattice which sits inside this region, and every atom that sits inside belongs to this rod. And the interatomic distance is epsilon k. For the sake of simplicity, also in this talk, I will just say it's 1 over k, and k is the parameter that is being set to infinity. So that's not a big issue. Now, what is a deformation? A deformation then really acts only on this lattice, and to each atom it assigns a new position. Right? To each atom here, it assigns a new position, and that's a lattice deformation. Now, what is the energy? I would like to treat a certain one. For example, next nearest neighbor interaction, also some bond angle dependent interactions. And there is a nice class of functions of energies that basically you can, I would call like a generalized mass spring models, which can be defined in the following way. So let's blow up one of these little cubes here. So we have here this cubes here with atoms sitting at all of these corners. And then let's see what happens if you deform this. So X bar is always my label of such a cell. X bar is the midpoint and the label. So this is basically, this is the position here of, say, so that's a 3 times 8 matrix. So the fourth, for example, the fourth column would be where the Z4 point is mapped minus the average over all these other guys where these are mapped. Now this is a matrix, it's a 3 times 8 matrix, and it encodes all the relative displacements of the cube. So this is the cube, you map it somewhere and you know all the relative displacement. This is like a finite difference stencil for such a thing here. Okay. Now my basic constitutive assumption is that I can write down an energy in the following way. I'm having an energy here. I'm summing over all the cells. So remember, this is the label of all the atomic cells. And I'm simply summing some energy which depends on the reference configuration of the new distances in the reference configuration. And every nearest neighbor and next nearest neighbor pair interaction, for example, can be recast in this way. That's not difficult to see. I also have some surface terms. because if I'm looking at finitely many layers, somehow the surface really matters. The surface can be of the same order of magnitude as the bulk for finitely many layers. But for this talk, I'm just neglecting it. We can do everything explicit for the surface, but I mean the formulas are getting incredibly large. So let me neglect these guys, and let me also only look at these guys here. Now then, what is the cell energy function? It satisfies a whole number of assumptions, but somehow I don't want to list them here. Let me just point out the most important features of this. One model you could look at would be a nearest and next to nearest neighbor model, where nearest neighbors interact via some Lennard-Jones potential, for example, and next nearest neighbors as well would interact via some Lennard-Jones potential. Yeah? Equilibrates, say, by 1 and square root of 2. Or this nearest and next to nearest neighbor, yeah? Now, this would be this case. So this would be Lennard-Jones potential equilibrates by 1, equilibrates by square root of 2. But now we have this modeling issue that we cannot, if I were to put just plain Lennard-Jones here, I would have the difficulty that if I do the dimension reduction, I will never see fracture, because it's too stiff. There is no aspect ratio dependent term in the energy. So this is why I cannot do this. If I really want to do something reasonable, if I want to see bending and curvature at the same time, I have to be in a regime where I introduce H-dependent material parameters. Meaning that I'm not looking at one fixed material, but at a range of certain materials to which this are, right? So, and this is what I'm doing here. So this is in fact a K-dependent energy. And this K-dependent energy is such that near the wells here, so if this is almost the discrete identity, then this is almost K-independent. Yeah, so at least, let's say it is K-independent in a small region around the identity. But if you have large entrances here, so large drains, then this will get weaker and weaker, and it will be something like scaling like 1 over K in our thing, which 1 over K is again the aspect ratio. And I do have a number of technical assumptions which I completely sweep under the rug here. Now, then, what is the task? The task is to define this gamma limit. So this is the atomic energy here, multiplying by this term. So this black part basically is the finite energy per unit volume. And then I divide by this power of h to the 4, because on one of the last slides I tried to convince you that h4 is the right power for the thin rods. So then I divide by this, and the main point is to seek a gamma limit of this structure. Now, of course, a gamma limit for this kind of discrete settings is in the end I would like to end up with something not discrete but continuum. I mean, I'm not precise here. I interpolate in a certain affine manner in order to speak of just normal L2 conversions, for example. So that's the topology in which I look at this gamma convergence. Now, let's first look at compactness. So here's this picture of a very strange cross-section, just in order to show off that it can be very fancy, right? So this could be a very fancy kind of a rod. But let's look at the particular case where we have a fixed, atomistically fixed rod, a fixed cross-section. So meaning that the cross-section in atomistic units is of fixed size. So this means you're looking into interatomic distances where basically the thickness of the film is a fixed multiple of the interatomic spacing. And in particular, this means we can treat the cross-section as just as being fixed, a union of squares, basically. Now then, here's the compactness theorem, which is not difficult. The compactness theorem is more or less easy. It simply works. So there's nothing, more or less nothing to it, because you can simply prove it by comparison to the case that Maria Giovanna and Stefan Müller did. And what we observe is the following. So you do converge. So these interpolations do converge. They do converge to W22, but at finitely many points they can break. At finitely many points they can have fracture. And so this is why you converge here to something which is only piecewise W22. And again, if you look at this gradient here and this rescaled gradient, so you have to rescale in the small film direction, in the small rod direction, then you end up with a rotation matrix here, saying basically that you're ending up with a limiting theory for an inextensible rod, and basically this it's like an orthonormal frame that here. So this is the tangent vector. This is y that traces the rod, and this is the tangent vector, and this is an orthonormal frame. This r which goes along the rod. Right? And but this tells you already the class of admissible configurations is the one that you know from continuum theory, but they can have certain. Okay. Now there's also here's the gamma convergence result. So let's do the gamma convergence. So this is what comes out. There are two parts, and it's exactly a little bit like this Griffith type of energy, but not quite. So there is an elastic part. So Q again is a quadratic form. So this matrix here, I'm not writing it down explicitly, but in this matrix here you find all the curvature and torsion terms. So this is an orthonormal frame. So this is R prime, and you have R transpose here. If you write down in coordinates, you would see all the curvature and torsion of the film. And so this is exactly the elastic bending and torsion energy that you would see. But then you have these finitely many jump points, and you get something which is this crack contribution. So note, in some sense, it's a bit different from it's higher order Griffith in some sense, because exactly here you're having elastic contributions. But here it's not only the jump of phi, so it's not only the rod can jump, but also there can be kinks, right? So, and this kink would be a continuity point of y, but a jump of the orthonormal frame. So it could be that the orthonormal frame just jumps without the jumping itself. Okay, and this is what we get. Now, in some sense, it has, it can all be, well, this elastic part, I should say, I would not talk too long about this, because this can be computed. This can be computed just explicitly. So we have explicit formulas also for the surface term. It's not quite, it's almost like, if you know the formula in the continuum, it's almost like the formula in the continuum. There is some kind of minimization you have to do in order to account for warping of the cross section, but it's only a discrete minimization problem, not a continuum problem in our case. And this matrix A is exactly where we now have to plug in our curvatures and torsion. But then there are some additional terms. I will not interpret them, but they are basically due to the discrete nature of the underlying lattice. And since we're only looking at atomistically thin objects, we see some discreteness effects there here. So some spurious discreteness effects. Otherwise, it's more like, basically, morally, it's like a continuum rod theory, as you would know it from the continuum. Now, let's go for the crack part. Okay, so the crack part, usually you can try to solve some in some abstract way, right? I mean, what would you do if you have something where you see crack? How would you assign a crack energy? Well, you would try to look into the crack, and you would try to blow up and see what's happening if I look there and then I blow up the crack. So then usually what you can do is you can write on some formula, but this formula is I mean, it has leaf subs and winds, and so you don't want to really see it, right? I mean, I was not sure if you want to see it, so I show it. Here it is. No, you don't want to see it. So I go back. But, I mean, the basic form is very easy. It's a very similar, familiar form to you. So what you need to do is you need to fix the values here. You need to blow up. You have to go where the crack or the kink happens, blow up, and then associate, I mean, some blow up cell problem where you have fixed boundary values given by these values here. So fixed to the left, fixed to the right, and then you let the energy decide what is some optimal way. Now this is actually not difficult, but there's a caveat, and the problem here is that precisely we need to take care of this K-dependency of the cell energy. So this can be nasty. So this K-dependency says that it's not automatically clear that if in this case you try to define if you have a well-defined cell formula if the limb inf is really the limb sup. So this is kind of difficult, and you need to work a little bit on the cell formula, but it can be done. And I'm not going into details, but I would like to show one point. So basically that's the scale dependency, which is necessary. It's inherent in our problem that we have something which is constant in this region, but decreasing in this region. But in the end, you also have to take, in order to blow it, you have to look at the k times of the scale, because you're looking at lower and lower energies. So that's what made life a little bit difficult. Let me just point at one specific application of this or aspect which made the proof in the end possible. And this is, okay, that's a nasty formula, that what we can do is we can prove that if we do the cell formula, and that's actually, I can show this in one picture only. If you do the cell formula, you have to have, I mean, it's like this. So here you have this, you have a kink, then you look inside, okay, here it looks like this, here it looks like this, and then in the middle you don't know. I mean, you want to connect these in a way which is energetically optimal. What could happen is that you introduce a little bit of crack here, and then something, and a little bit further crack here, and this is very nasty if the crack is getting too far. So what you would like to see is that, in fact, all the cracks that happen in a very small atomistically confined region. And this is, in fact, let me just show a picture how we do this. So here you fix the boundary conditions for the cell problem. Now, if you really had a large region where fracture happens and also elastic region there are, then it's always possible to take these, so that's, in fact, they're not bent like this, they're blown up, they're just bent a little bit, yeah, so this is just in order to see something on the slide. So you can rigidify here and here, make this piece straight in some sense, and then cut out here and glue it again to this in order to achieve this larger dark gray region. Well, if you do this, you introduce a little bit of error, but in the end, this can be estimated away. And in fact, what you see here, instead of this large region, you have considerably made this guy smaller here. And again, if this guy had been too big, you could rigidify here in the middle. And once you are completely rigid, you put it to the boundary values. And such a construction in the end made it possible to show that, in fact, it's optimal to have cracks only located in an atomistically confined region. Okay. So that is as much as I wanted to show concerning the thin rods. Now, somehow a quite more challenging problem is to look into plates. And this is what we're doing now. And somehow here the results, we also tried to do something in an atomistic setting, but for some reasons this did not completely work. So I'm switching a little bit to a very much related continuum problem, which we hope later to also, match with some atomistic modeling. But for the time being, let me look into some purely continuum setting. Now, I'm switching gears a little bit, but the basics, the limiting functions will be similar. So instead of looking into something which is which has weak rods and weak atomistic interactions, I'm looking into some elastic matrix, and there can be voids forming. And of course, if I have voids, then to the left, to the right of some voids, I can have completely different deformations. So these voids can introduce cracks. And then, this really has applications, for example, if you have some membranes which can go some degradation, and then in the end they form this, and then you will find that they can tear apart and different stuff. Now, the problem is that I would like to find an effective theory again for membranes and plates also, which accounts for some elastic matrix in which there can occur some very small voids and cracks. Now, the situation is not very good as concerns literature. So there are some results basically in a linearized setting, and there are also some recent results here by Janusz and Peter, for example, on a linearized setting. Starting with the non-linear parent regime, the situation is not very good. I think there are some results on membranes by this Fonseca, and in the quasi-static setting by Bernd. And I myself did something, but only in a 2D setting for plates. This is basically the starting point. Here is the model. So this is the reference configuration, right? and this is the energy. So this is again completely elastic here, but I'm having a number of voids. So you could just imagine this is some kind of Swiss cheese, right? Do you want to deform elastically? So you pay elastic energy here, but on the voids you don't pay anything. But what you do pay is you do pay surface energy if you introduce voids, and this is exactly this guy here. Now this now can be very general, and then this psi should always be a norm. Now, of course, you could think of this first in the bulk. Before we do thin plates, let's just see what's happening in the bulk. Now, if you look at the relaxation, the bulk relaxation of this problem, this has been done already a number of years ago. So what's happening is that basically this elastic part decouples. You can just take the positive envelope here. But for the voids, something can happen. So for the voids, it could be if you just to minimize it. This is just the L1 relaxation. For the voids, it could be that this, since psi is a nice norm, that this term just survives. But a further thing can happen. So during the relaxation process, voids can collapse, right? So they can form a tubular neighborhood of a, let's say here, of a 1D structure, and then they can collide, and to the left and to the right of this guy, the deformation can be completely different, right? So this is why along codimensional 1 surfaces in the relaxation, when you have relaxed the problem, you can have jumps. And so if you compute this relaxation, the domain will now be in a SPV space, and you will end up with such a function in here. And where does this factor 2 come from? Well, it comes precisely from the fact that if you have a crack and you want to approximate it by a void, then you have to go 2 sides, right? And so you have to first go from the matrix into the void and then from the void in the matrix again, so you pay twice the surface. Okay. Unfortunately, we didn't know this. We proved it again, but then we realized. I think only the introduction was not yet written. Then we realized it had been proven. Okay, so then, well, in the end, for us, it was an auxiliary site because we actually wanted to do membranes, and this is what we did for membranes. So if you do the same now for membranes, you say it's exactly the same setup as before, only that this should be a capital S, I'm sorry, not a small omega, only that we're looking into thin films. If I try to do a dimension reduction analysis for this guy, well, what should I do? Without these voids, this has been done long ago by Ledrette and Raoult, yeah, and what you should do is, they tell you what you should do is, you should define a new energy density here where you minimize out the small x3 direction, because this is what you do not control anyway. And well, if you do this now here also for this psi, if you minimize out and you define a new psi here, then this is exactly the right thing to do. And then you can prove gamma conversion to such a function. It's exactly the same formula. It's exactly the mixture of the previous bulk relaxation result plus Ledrette. No surprises there. Except, so and it's not so difficult to prove. The only difficult case to prove is really that if you really want to get this term right in the relaxation, you have to be careful a little bit because this energy can be a little bit different. Okay. So far so good. This works. So now let's come to the maybe a bit more challenging part. Well, the more challenging part is somehow if you now look into plates, because yeah, what can we do for plates? So for plates, this is exactly the same setup I had before. So exactly the same energy functional. It's exactly the same as we had for membranes, but the only difference is that I put this H-dependent term here. It again says that this accounts for the small H-dependent fracture toughness. That's exactly the term where I put it here. And then it's exactly the same setup as for membranes, but only we have this more specific assumption on a single energy well at this. Okay. Now, then what you should do if you would like to calculate or compute a gamma limit, you should divide by the appropriate powers of H. And if you do this, you end up with a rescaled energy functional, which looks like this. Yeah. So I've divided here by this H squared, where there's one H One division of H you don't see because I also passed to this domain here. I did a change of variables, and I'm having this this rescaled gradient here. I'm having this rescaled crack normal here, and then I'm getting this small 1/h² in front of the bulk part. Now again, what Ledret and Raoult did here by minimizing out the third direction, we do here, as Friesike James Müller, for example, also do in the pure Kirchhoff case. You minimize out what happens in the x3 direction. That's exactly, we do this now here for the Hessian. That's exactly what we did previously for W. And in this way, we define a new two-dimensional relaxed quadratic form. And if you know this works by Friesike James Müller, you recognize this is exactly the term that they get. Yeah. Okay. And yeah. Now there's one issue, however, and if you recall what Friesike James Müller do is they derive something which is finite over sets of isometries. And now that's a bit more difficult now, because now we can have cracks, and we have to think about what is the right space where this should all live. And our point is the following. We propose the following space. So what you should look at now is you look at SPV spaces again. So basically, this will be the midplane now. I mean, the finite, the film deformation. So what is the film deformation? It takes this midplane S and maps it to R3, right? So it is a mapping. So I'm sorry, now the midplanes are called omega here, little omega. It goes into R3. We also assume it's bounded. That's fine. And in such a way, so SPV2 this 2 just means that this absolute continuous part here is square integrable, and also that the length of the crack is finite. And so that this absolutely continuous part of the gradient is itself an SPV function, right? And first of all, so you can take this absolutely continuous part here, you can complete it to be something in SO3. So meaning that this guy here is actually in O23, right? I mean, it's in so this R, if it were all smooth, it would be just an isometric inversion. But it has higher regularity, and the higher regularity is in the sense it's not W22 anymore. So the W22 is now replaced by the fact that this absolutely continuous part of the gradient is itself an SPV2 function. So in fact, well, I will come to this. So then you also have to define the curvature term, and the second fundamental form we do now is exactly the right formula that you know from the Sobolev case for the W22 case, but we only take into account the absolutely continuous contributions here. So this is the absolutely continuous contribution of this guy here, and since this is itself an SPV2 function, so it has a second gradient, again, an absolutely continuous part. So we look at the absolutely continuous part of this guy here, and this is exactly these contributions here. So that's our definition of the second fundamental form. And in terms of this, we define the following generalization of the Kirchhoff energy functional, and this should be the following. If you look at the first line here, and neglect this D here, it's exactly what you know from Kirchhoff's theory. It's exactly the 2D here over the second fundamental form, right? But then you have additional contributions. So again, there is this easy additional contributions for voids that survive. And there's another crack contributions for voids that collapse into a single crack. And again, well, why don't we just call it a Griffith term here? Because in some sense, as for the rods, there are two ways you can introduce cracks. So you can have a crack of the field R itself, because this is an SPV, so you can have a crack set. But also the gradient of R itself can have a crack. So in fact, what we integrate here is over the crack set of R and of the gradient of R, just as you would do in this Blake-Sisserman formula where you penalize jumps in R and kinks and jumps in the derivative of R, right? And then, but apart from this, you get exactly the energy that you would expect. You get again the psi naught, and the psi naught is exactly again the small film direction minimized out psi that we had in the previous talk, in the previous slide. And if we do this, well, we have sort of gamma convergence to this limiting model with, I have to introduce at least one extra condition, but let me state it as these are the main results. So now, of course, the question is, does this guy, I mean, this energy function, is this the limiting function of the gamma converge of the gamma limit? And in fact, it is. Well, what we do is we do only treat bounded deformations, but this is, I think, more or less okay. You can put yourself in a lab, right? Your lab is bounded anyway. So, you can have this lower bound. I mean, but there's another point. We do have what we term a minimal droplet assumption, and this is an assumption that there can be small droplets of the film, there can be small voids, but there cannot be too many small voids that are much smaller than the film is thick. That's the main assumption. I will come in the next slide. I will comment about this. And then there are matching upper bounds. So this you can also get. You can match by upper bounds. And also okay. Compactness. What is to say compactness? Well, if you have bounded energy and you're also in a finite laboratory, then you find minimal convergence, subsequential convergence. Well, the voids converge perfectly, but of course, inside the void regions, you cannot converge. There's no coercivity inside the voids. You cannot expect that the deformation converges inside the voids. It only converges outside the voids. So this YH converges to this limiting R, but only outside. But that is not a problem, because if you look back, this energy doesn't care what is inside the voids, right? So this is the right notion of convergence. We do not need convergence inside the voids. That's not important. So this is why we get this, why this is the right assumption here. So let me end by making following remarks. Well, what is this kind of minimal droplet assumption I mentioned? So this is the void set in the rescale picture. These are the voids in the physical picture. You're absolutely on the safe side if you have such an assumption here. If you know that the second fundamental form of all the voids is bounded and by a divergent bound only. So it can be so the fund can be verse and verse scaling with 1/h. So eventually this condition vanishes. So just 1 minute. Eventually this condition vanishes. But our condition is a bit more general. We don't need a pointwise. We can have a more general. But if I write this down, it's a bit long formula. Now let me say that also infinity bound is not really a restriction, because you can also implement it in the recovery sequences, and if you want, you can also implement it in the energy functional. Put the energy functional plus infinity if you're outside the lab. And then finally, of course, it's interesting to know that if you have a bit better set, so not only finite perimeter, but really finite Minkowski content, then you can even find uniform bounds on recovering void sets which satisfy the minimal droplet assumptions. And with this, I would like to thank you very much.